Assalamualaikum and a very good day, guys. So, currently we are in this week 6, and this week going to be our last session for the first order ordinary differential equation. And for today, I would like to expand further on the application of ODE for the nonlinear differential equation. And before we started, I have to say I I have to say that this is gonna be a tough week for me because I have misplaced my um, pen tablet. Then it just that will limit me somehow for the solution part. All right. Okay, guys. Let's get started. All right. I will cover for the nonlinear model. The first one is the population dynamics. So usually the population dynamics is we will discuss in context of biology, and then the second one is draining a tank. The tourism is low. Right. There is a numerous application that can be modeled by using ODE that are nonlinear, but we can transform it to the linear differential equation. And then previously we have learned on the population, but uh, in the previous in the previous uh, application for the population that we have been studied and discussed uh, is the simplest model actually, as we compare to what we're gonna learn in this population dynamics, right? Okay, population dynamics is a field that models models the evolution of population of plants, animals, or human over the time, and we predict the growth of a population, and then differential equation uh, can be used to represent the size of a population over time. So we saw this in an earlier uh, earlier lecture in the section of exponential growth and decay, uh, which is I think the most simplest model. And however, a more realistic model, we must include other factors that affect the growth of population. So previously we have learned on the exponential growth and decay. We only touch about the birth and the death, the growth and the decay, but we are not concerned on the other factors such as the what we call by the other factors such as the what we call by uh debt rate, food supplies and so on. We are not consider about that in uh the previous sorry, in the previous uh in the previous lesson. All right. In this topic, we will cover and study on the uh, logistic differential equation, and we're gonna see how it applies to the study of population dynamic in the context of biology, especially. All right. So the model that population growth using a differential equation, and we first need to introduce some variables and relevant term. The variable t especially will represent the time, and the unit can be, well, our days, week, month, or even years. And any given problem must be a specified unit used in that particular problem. Since the population varies over the time, it is understood to be a function of time. All right. So usually I use the notation of dp, dt, or p, uh, p of t for the population as a function of time of the population. Okay. Well, if pt is a differentiable function, then the first derivative dp dt represent uh, the rate of change of the population as a function over time, right? In exponential growth and decay, that what we have learned in the previous lesson, we study on the exponential growth and decay of population and radioactive substances. So, uh, but this differential equation um, has an interesting interpretation, all right? Whereas the rate of which population increase or decrease uh, is equal to a positive constant multiplied by the current population. Therefore, the DE rate at the population increase is proportional to the population at point of time. This what we have learned in the previous um, lesson. Okay, I just recall it back so that you can compare what is the difference between the growth and the exponential growth and decay that we have learned previous session compared to this population dynamic or logistic differential equation. Okay, and then one problem that not discussed in the previous lesson is the prediction. As the time that goes on, the population grow, actually the population that grows without a bound. This is unrealistic in a real world setting, whereas actually there's a various factor that limit the rate of growth of a particular population. This including the birth rate, death rate, the food supply, predators, and so on. So the growth usually take into consideration the birth and death rate, but none of the other factor it can be interpreted, okay, from the previous lesson. And then it is uh, and then the population grow. It is find that the population grows until a certain uh, steady rate. So previously, for the exponential growth, we learn this is the graph. Okay, so I have to use the mouse. So usually this is the growth, the exponential growth, what we have learned in the previous subtopic, subtopic lah. Right. So currently, what we're gonna learn is about this graph. Okay, we will learn how that we found the population grows until a certain steady state population is reached. Okay, so there is difference between these two. So currently we will learn on the population that grows until a certain rate and it becomes a maximum population. Okay, and then it's constant at this rate. So we will learn about this on the population dynamic. And then, however, uh, this is what we call by steady state population. And then this possibility this possibility is not taken into account when we learn about the exponential growth previously. And then we will learn on the concept of carrying capacity that allows for the possibility that in a given area only a certain number of a given organism or animal that can thrive without running into resources issue. So the carrying capacity of an organism in a given environment is defined to be the maximum population that organism that the environment can sustain. All right. So this carrying capacity, uh, we can define it as to be a maximum population. Okay. And then the growth rate of this it depends on uh, what variable that we use. So and then by using this variable we can define the logistic differential equation. Okay guys, I hope at least you have mm, a, a brief review on the what is the carrying capacity, what is the logistic differential equation, and then what we concern on the logistic differential equation, what is the difference when we compare from the previous exponential growth and decay. All right, so I will um, I will let you watch the video on the population dynamics later on related to the logistic differential equation, and I mean the idea, the concept of this, because I can do nothing because I think it's uh, when my pen is missing, I think it's limited for me how to explain to you about this thing. All right. Well, okay, before we go to the basic idea of the video and from our source video, I would like to uh, I would like you we have to complete this slide first. Okay, this population dynamics we use to predict the growth of a population. Okay, the differential equation is the predict. We want to predict the growth of population over the years, let's say over 5 to 7 years, and then we want to know the growth rate for this kind of population. Then the logistic equation, usually this is the logistic equation, right? dp over dt equal to p a minus bp. A and b here are constant, okay? That is mass larger than 0 and b mass greater than 0, right? Where p is the size of population over the time with respect of time. Right. And then the solution of the logistic equation. This is the solution. And I think I think I just use this equation um, find how we rather than we find how we gonna get this logistic equation. I believe that we just use this equation, and at least you have an idea how you're gonna use this equation, right? So let's go to the video, and then from this video you will understand further on the what is the carrying capacity and how we gonna define the maximum uh, population of that organism, where is the steady state of the population dynamic. All right, guys. Okay, we go to the next slide. Right. Let's have a look for example number 2. Okay. For this example, we are given the number NT of people in a community. So that means we are using notation N here as a population and who are exposed to our particular advertisement is governed by the logistic equation. Okay, so here we can highlight for the logistic equation. Okay, initially n when t is equal to 0, n is equal to 500. So this is the number of people in the community initially, right? And it is observed that when n is equal to 1, it's equal to double the amount, which is 1000. Okay, so for NT, if it is predicted that the limiting number of people in the community who will see the advertisement is 50,000. So they are predict that the number of people that will see the advertisement is 50,000. So we have to solve for NT. Okay, and here is the logistic equation. dp over dt equal to pa minus bp. So in this problem, we change it to dn over dt equal to n a minus b n. Alright, so we just use the solution instead. Then we derive it. You just use it because it takes time for you to derive. You just use the solution for the logistic equation. So a and b here is a constant, and here is the initial n naught. Here is the initial, which is 500. Okay, and a and b is the constant. All right, so here is the solution. So when t is equal to 0 and naught is equal to 500. So just plug in the 500 inside this one. Okay, let's see how this is the first equation when you plug in the 500, and then when t is infinite, okay, n is equal to 50,000. So we substitute t as an infinite. So here is 0 and 500a over 500b. Okay, this is the second equation. And then we just use this. A is equal to 50,000 B. Alright, so this is our second equation. Then for t is equal to 1, this is the given in the equation. And then just substitute equation 2 and into the equation 1. Okay, so we just put n is 1000 and t, here is t, right? So t here is just s1, okay, and then a is given here. I just substitute a here. Okay, here is a, and then here is a minus 500 b. Okay, you just substitute here. So here is 500b. Right. So here it is, and then you just solve this. Okay, solve for b, that will obtain okay, when you solve this, you get b, you simplify it, you get b is equal to negative 1 over 50,000, and then 49 over 99, which is equal to 0.000014. All right. Well, and then after we solve for B, we have to solve for A. So you just substitute the B value, and then inside A, so you get the value of A is 0.7033, and then we substitute back for the in the general solution that we have been obtained previously. Well, just substitute it back here. Okay, it's a 50,000 over 1 plus 99e. So here is 0.7033 is a t. Okay, so this is um, how we supposed to do um, the 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 solution method for the population logistic equation. We try to find the constant value, which is a and b, and then after that we substitute back to the general solution previously, and then, well, this is the DE that we want, the differential equation, the solution for the differential equation. All right, guys, so we go to the next subtopic or slide. Thank you. All right, guys, one of the most common application in the first order differential equation is the draining tank problem. All right, so a tank that such as so this is the tank here, all right, is filled with a liquid at time t is equal to 0. So this tank is filled with a liquid at time t is equal to 0. A drain in the bottom of the tank is open. So here is the hole. Alright, so the tank begins to, what happened next, to empty. So this is the concept of this application. Alright, so this is the drain area, right? So hash here is the height. Okay, hash here is the height different. Hash is the height different between the water level and the level where the water is drained or leave. Okay, so here is the height, this is the water level, and where the water is drained. So here is the water is drained, so here is the hash. Okay, alright, so what is AW here? So as you can see, here is I denoted here is AW. What is the meaning of AW? Okay, so AW here is the area of the surface area. Okay, this is the surface area, this is the surface area of the tank. Alright, however, AH, so here is AH. What is AH here is the surface area of this hole here, or the bottom of the tank where it is open, the drain area. I would say the drain area. Alright, so if there is, here is the drain area, you will have velocity of the water that draining at time. So v is velocity or the speed. Okay, so the capital V is the volume, and V here is the speed, or we can call it V here is a efflux speed. Okay, efflux speed. Efflux speed. Okay, of water through a sharp edge hole at the bottom of a tank that filled to a depth of h. Okay, so speed of a body. Okay, this efflux speed is similar with the speed of a body that falling free fall from a height h. So we assume that this efflux speed v here is similar with the speed when there is body fall from the height h. Okay, well, you can get this the same equation by using the conservation of energy. So this is the equation, the efflux speed previously, because we consider it's a free fall from the height, and then you can get the same equation using conservation of energy. Okay, so as the fluid descends, whenever something falls, the gravitational potential energy, okay, is decreasing. Alright, is decreasing, that the gravitational potential energy converted to the kinetic energy. So this is the conservation of energy. Okay, that means the kinetic energy is equal to the gravitational potential energy, because it's convert as the fluid shoot out. Okay, when the fluid shoot out of the tank. So in this example, we said that kinetic energy is equal to the potential energy, where this is the kinetic energy formula, and this is the potential energy formula. So we can get the we can derive this speed efflux or velocity here. So this velocity is we can get it by using the conservation of energy. Okay, or we can use the Bernoulli equation. We can get the similar speed by using Bernoulli equation. Okay, so there are many variables that involved in this problem. Okay, where is the surface area of the drain? Suppose that we want to know what will be the height at time t. Alright, so this is the volume. V here is volume, okay, the capital V. So volume of water leaving the tank through the hole will be, here V is equal to A sub h and 2gh, right? So A sub h and square root 2gh, and then from this equation here we can get it, we can derive because the volume will change over the time, so we can derive it dv over dt And then negative sign here means that V is decreasing, right? The volume is decreasing because the water will leaving the tank. Okay, so there is negative here. A here is the area of the hole. Okay, this area of the hole. So A sub h, right? And then square root to G here is the gravitational and force, and then h here is this one. Okay, all right. So volume of water in the tank at time t will be, so if we want to find the volume of water at time t, let's say we want to find the volume of water that inside the tank. So we use this derivation here, derivative here, right? So whereas AW is this this surface area of the tank, okay, and then times by h, right? Time by h. Okay, this is the volume of water inside the tank, and here is the volume of water that leaving the tank. So can you see the difference? Okay, so it's still similar, the volume is still similar. And then the sign, how about the sign? Is AW have the sign negative as well? Alright, the sign will be because AW you don't use the negative sign, so we can cancel this here, right? Why we don't use the negative sign? Because AW is the water in the tank that is not leaving the tank. That means we are using this equation here, right? And then what next? So here it is, how we gonna substitute the second equation into the first equation previously. Alright, so we have to substitute here a dv dt. So previously we have 2 dv dt. This is the volume of water leaving the tank, 2gh. And then we have a second equation here, dv dt equals to AW dh over dt. So this is the first and this is the second. Alright, so we have to consider both of these is equivalent to each other. Alright, and then don't forget the sign here, and then we want this dh dt here, and then we arrange it by negative ah by equal negative a sub h square root 2gh over a sub w here. Alright, so this equation 3 is valid even if the surface area AW is not constant. Alright, so we can use this equation here for any shape, such as a conical shape that is not even the surface area is not constant. For the conical shape, you know, conical shape is like this. Okay, we can use this equation as well. And however, to obtain DE, differential equation, the surface area of the water must be expressed as a function of h. So that means AW equal to a sub w is equal to a h here. So this one you can see from the next example. I think this is not the example number 2. Sorry guys, this is I think this is the example number 4 for the conical shape. Alright, okay. Okay, we go direct to the example number 3. So if you are given a tank, okay, in the form of right circular cylinder standing, okay, that means this is your tank, okay, right circular standing, and on the end is leaking. So you have a leaking water to the circular hole in the bottom here, okay, ignoring friction and contraction of water at the hole. Then the height, okay, let's say this is the height of the water is described as this. So you are given this what we call by this equation here, what say this is the height, okay, where a sub w and a sub h are the cross sectional of the water, so a sub w, and the whole a sub h cross section of the respectively. Alright, then solve the differential equation if the initial height of the water is h. This equation, this question here means that where t is equal to 0, so h t is equal to, that means h 0 is equal to h. Okay, we are given 32 feet over square s square here, right? So we are not gonna use g 9.81 meter per square. So we are use feet over second square here. Alright, so from this equation you are only given this equation and this one. So how we're gonna solve this is you're not given any what you call by numbers here. So that means how we're gonna solve this example A. We go to the next slide. Alright, here it is. So solve this differential equation if you are given g here. So this is the equation that is given to us, alright, and then you substitute you plug in any variables that that are given to you. So g here is given, right? So g is 32 feet over second square, and then 2 here is here, alright, so 64 hash. So finally you, for d hash over dt, you have this equation, and then from this equation a hash is constant, aw is constant, so at here is constant as well. So from this equation, can you do the separable variables method here or any other method that you can solve this, right? So in this case I arrange AH over AW8, and then as integrate dt here, and then square root hash. When you transfer to the left hand side here, I get this negative, okay, negative 1 over 2. So that means hash negative 1. So that means when I transfer square root hash, we get hash and then 1 over here. So this means hash negative 1 over 2 here, right? And then I integrate both sides because we are using separable variable method. And then what do we get after we integrate? Here is 2 square root hash is equal to negative at a sub hash over a sub w times t plus c. Alright, I hope you you know how to get this. This is the basic basic problem, basic integration. Okay, and then because we are given the initial value of hash t is equal to 0 previously and then equal to hash, so we just substitute t here equal to 0, so you get here 0. So here you get 2 over hash, sorry, so here you get c is equal to 2 over, not 2, 2 times hash. Okay, we substitute here, right? So finally this is the value of c, and then you just plug in the c inside this equation. Okay, you just plug in and see what you will get after you plug in the equation. Alright, so here means after I plug in the equation, so I will get this one here. So 2 hash is equal to negative 8 a hash over AW, okay, plus 2 hash. Okay, just plug in and you try to rearrange it. You get you bring it here, so you get divide by 2 is 4, so you get here negative 4 a hash. Okay, so here you get hash t is equal to negative 4 a hash, and then so you don't forget t here, okay, because this one, so t, and then plus plus AW, because here you must AW over hash. Okay, you multiply by AW here, and then AW over hash, okay, over AW square root, and here you get square root as well. Okay, so here how you will get this one. Okay, so this is how we're gonna solve this kind of problem. Okay, next we go to the question B here. So we are given the tank height, right? So suppose the tank is 10 feet high, so that means hash, not hash equal to 10 feet, right? And the radius n has a radius, so a radius of is equal to 2 feet, and then the circular hole, so r sub hash, this one r sub w is the one that AW, okay, and then r sub hash is the radius water, and then the radius hole is a half inch. Okay, half inch is equal to 1 feet is equal to 12 inch, so you can divide by 12, forget the divide by 12, so you get 1 over 24 feet. Okay, alright guys, then from this equation, from the previous equation that we get, you just substitute, you know, the area is equal to area of water is equal to pi r squared. R is given, RW is given is 2 feet here. Okay, so you get here 4 pi, and then a hash is given 1 over 24 feet, right? 1 over 24 feet here, pi, so a hash is given. Alright, so we are given hash is equal to 10 feet as well. Okay, then what you're gonna do is you have to substitute one by one. Okay, so this is a capital. Okay, you have to substitute one by one inside here, and then you equal to, because the question is how long will it take to empty. Empty here mean hash t is equal to 0. So we want the time here. So hash t, we just substitute hash t here is equal to 0, because we want the tank to be empty, but we want to find this time here. Okay, and then you have to substitute a 0 is equal to, so here 4 pi over square root 10 minus pi over 144 t, okay, over 4 pi square. Okay, so you will find, well, where did I get 144 here? So it's from when you substitute and you plug in AH inside this equation here, you will find 4 divided by 576 is 144 here. Okay, and AW here is 45. You just plug in inside here. Okay, over square root times square root of hash is 10, and then 4 pi squared. Um, so this is how you're gonna solve this. Okay, and then you transfer this here is 0, so you will get this 4 pi square root of 10, okay, minus pi over 144 t, and then you have to transfer to the left hand side to make the t is positive, so you get this. Am I right? And then t is equal to 4 pi square root 10 over pi times 144. You cancel this out and you will get t is equal to 1821.47 second, or when you convert this by minute, you get 30 minutes, approximately 30 minutes. So here is how you're gonna solve this, right? So this here is the reference. It's similar step by step what I'm doing just now. So this is just reference for you how you're gonna solve this kind of question. Okay, all right, we move to the next example. Okay guys, try to solve this exercise. Okay, this exercise is you are given the low constant of the outflow of water from a cylindrical tank with a hole at the bottom here. Okay, so you are asked to find the height of water here, height of water in the tank at any time if the tank has a diameter of 2. So this is the diameter of 2 meter. Okay, the hole has a diameter, so the hole diameter is 1 cm. Okay, and the initial height of the water when the hole is open, so the initial height, so T hash T is equal, so initial hash O is equal to 2.25. Okay, when will tank be empty? So we want to find T here. Okay, try to solve this exercise, and I will give you the final answer for this exercise is T. So this is the answer. T is equal to 12.6 hour. Okay, try to solve this kind of exercise, and I'll give you the answer of the time. when will the tank be empty? When you are given when when the tank is empty is at time 12.6 hour. So try to solve this exercise. Alright guys, I think that's all for the application in the first order differential equation. So this is my last slide. Um, my last slide um, for mathematics engineering 2. And after this, Dr. Norazanina will continue with the second order ordinary differential equation. Alright guys, I wish you all the best in the test for the or in the final exam for the mathematics engineering 2, and thank you very much for your attention. Okay, and thank you for everything, and until we meet again later. Alright guys, thanks and all the best. Bye.